Alright, today we're going to be talking about the mole. It should sound very familiar, and so we'll look at its application in stoichiometry, limiting reactant problems, and percent yield. Just a reminder, the mole is Avogadro's amount of a substance, and Avogadro's number is 6.02, 2 if you want to use 4 sig figs, or just 6.02 times 10 to the 23rd. The unit here is given as mole to the negative 1, which is the same thing as 1 over mole. Okay. All that is saying is this many particles per mole. For example, if you have a mole of neon atoms, that is going to be that many, 6.02, 2 times 10 to the 23rd neon atoms. That is also equal to 20.18 grams, and this value is the substance's atomic mass from the periodic table. But instead of AMU, if you have 1 mole of the substance, its mass is in grams. If you had 1 atom of neon, then the mass would be atomic mass units. Similarly, if you have 1 mole of chloride ions, you have Avogadro's number of chloride ions, and the mass is 35.45 grams from the periodic table. Notice that chloride has a negative 1 charge, so that means it has gained an electron. Gaining an electron does not change the element's mass, because electrons have very insignificant mass, and it also does not change the number in Avogadro's number. We're talking about that many ions. The only thing that changes is the number of electrons, which is not what we're counting here. We're counting the actual number of chloride ions. So what is the mole? Okay, it's that many particles, but why is that significant? This allows us to count particles on what we call the macroscopic level, because the microscopic level, which would be the individual atoms, we can never actually count those. But using the mass, we can have an idea of how many atoms there are on the macroscopic. That's the level at which we do labs, or at which we see with the human eye. So this allows us to count because we know if we have 20.18 grams, for example, we have that many neon atoms. And if we have 10 grams, then we have approximately half as many atoms. So we're allowed to draw connections then between the macroscopic experiments that we do and the atomic level chemical processes that are actually taking place. So we're taking the macro that we can see in grams and relating it to the micro that we can't see, which would be the actual number of the atoms. Molar mass, the mass of a substance at the mole level, is equal to the atomic mass from the periodic table, but again, instead of atomic mass units, we're talking about grams, and the units are grams per mole. So for carbon dioxide, we would look at carbon on the periodic table, 12.01, oxygen, 16 times 2, add those together, and you get 44. That is 44 atomic mass units if we're talking about a single molecule, or 44 grams if we're talking about a mole of those atoms. So we can say that 1 mole of carbon dioxide is this many carbon dioxide molecules. Notice the use of the term there. It's not atoms of carbon dioxide, because carbon dioxide is a molecule, and that is also equal to 44 grams. So these facts can then become conversion factors that we can use to do all sorts of calculations. For example, how many moles of sodium chloride are there in 48 grams of sodium chloride? Now I want us to look at a mole map, and this one's going to be a little bit more detailed than we may have previously seen. Let me flip to that. Okay, so here is the mole map that I want you to see. This mole map features all sorts of stuff that we'll cover throughout this year, but I just want to kind of focus in here. So you should have a copy of this, so you don't have to jot all this down. The first thing I want to say is that these fractions that are given in the mole map are not necessarily turned the correct way. So depending on which way you're going, you may need to flip the fraction so that your units can cancel. For example, if you're going from moles to volume, which is liters, if you were going this way, then this fraction would work because liters would be on the top and moles would be on the bottom to cancel. But if you were going from liters to moles, then you would need to flip the fraction so that moles would be on the top and liters would be on the bottom to cancel. Right? The next thing I would say is that if a chemical reaction is not involved, then we're just going to be dealing with one side of the map or the other. So if there's no chemical reaction, then we're just looking at these sorts of conversions, okay? One side of this map. However, if there is a reaction involved and we need to cross to the other side, then we're going to need the molar ratio, and this molar ratio has to come, remember this, the molar ratio has to come from the balanced equation. So in order to do conversions where a chemical reaction is involved, we're going to need a balanced chemical equation. Okay, so we'll flip back and forth to this map as we look at these practice problems. So in this problem, it says how many moles are there in 48 grams? So if we look at the map, we're going from grams, which is our mass, to moles. Excuse that yellow box. We're going from mass in grams to moles. Okay, so we're looking at mass to moles, and it says to use grams over mole. Now, we know this conversion is turned the wrong way because we're trying to go to moles. So we're going to be doing moles over grams, but that gives us an idea of where to start. So if we look back at your notes, we're going to start out by writing down what we're given, which is our 48 grams of sodium chloride. And then we're going to use that fraction, but we're going to flip it over. So it's going to be 1 mole of sodium chloride over grams. So moles over grams. This is what you're looking for, moles. And this is what you need to cancel, grams. Now, how are moles and grams related? They're related by the molar mass from the periodic table. So you look up sodium, which is 22.99, I believe, or 23. And then we look up chlorine, which is around 35.4445, something like that. And we add those together and we get this molar mass. So to change grams to moles, we're going to do 48 times 1 divided by 58.44. And we find that there is 0.82 moles of sodium chloride within 48 grams. Okay, going the other way, how many grams of C2H6 are there in 18.7 moles? So we're starting with moles and trying to go to grams. Notice there's C2H6 only involved in this problem, so there's no chemical reaction involved. So if we look at our map, we're going from moles to grams. So we're going to use grams over mole. And we'll leave it as grams over mole because we do want to get rid of moles, so we need that to be on the bottom to cancel. So if we set this up, it'll be 18.7 moles times, we're going to put grams on the top, moles on the bottom, and how are they related? They're related by that mass from the periodic table. So 2 carbons and 6 hydrogens is around 30 grams over 1 mole, and those moles cancel. So we multiply and divide by 1, so that's around 562 grams. Next problem, how many water molecules are contained within a 56-gram sample? So we're given grams, and we're looking for molecules, and we're talking about water and water. So no chemical reaction is involved here. We'll look back at our map. We're going from grams to molecules. So if we look at the map, we've got the mass we're trying to figure out the particles. Okay, notice there's no direct link, so we're going to go from grams to moles, and then moles to particles. Now for grams to moles, we're going to have to flip this, because we want grams to cancel, and then we can use this one to get our moles to cancel, and we'll end up with particles. So to set that up, we've got 56 grams. Now we want grams on the bottom to cancel, and then we're going to have to go to moles first. So 1 mole over the molar mass of water. That gets us to moles. Now we want to go to molecules. So 1 mole on the bottom, and Avogadro's number of molecules on the top. Notice the cancellation that takes place, leaving you with molecules of water. And there's the answer, 1.9 times 10 to the 24th. Now remember to put scientific notation in your calculator. Whenever you see times 10 to some power, you're going to press EE on your calculator and then the exponent. So you would press 6.022. Do not press the times or the 10 button, but rather just press EE and then 23. And this should be written on your calculator as 1.9 and then a 24 as the exponent, which you have to translate that into 1.9 times 10 to the 24th. So make sure you can do scientific notation in your calculator. That's kind of a key skill, and you'll be way off track. So let me know if you need help with that. All right. This next question says, how many hydrogen atoms are contained within a 56 gram sample of water? Hydrogen atoms, 56 grams of water. So we're still trying to go from grams to particles. We're thinking about the map. We're still going from grams. Pull that again. We're still going from grams to particles. So we're taking the same pathway, but this question's a little different. Instead of wanting to know how many molecules of water there are, they're asking how many hydrogen atoms there are. So let's look at how to approach this. We're going to start out the same way. "56 grams of water." We're going to get grams to cancel by going to moles using the molar mass. We'll then cancel moles and use Avogadro's number to go to molecules. But notice we can't stop here because this is molecules of water, and the question is how many hydrogen atoms are there? So we have to think about how many hydrogens are there within water. There are 2 atoms of hydrogen in every 1 molecule of water. So we can use that ratio as a conversion factor. So if we're asked to find the amount of some atom within the molecule, then we'll need to use a ratio showing how many of that atom is within the molecule. And that will allow the molecule to cancel and help me find how many atoms there are. Again, I would make sure that you can put this in your calculator and get this answer that is given, 3.7 times 10 to the 24th. Now, what if a chemical reaction is involved? Okay, that's going to require us to have a balanced chemical equation, and we're going to need to go from one side of the mole map to the other if we're doing a calculation. So first off, it's really important that in a chemical reaction, atoms are conserved. This is the law of conservation of mass. It says that atoms cannot be created or destroyed. So you see in this example, on the left-hand side we have 1 carbon atom, and then on the right-hand side we also have 1 carbon atom. 4 hydrogen atoms, 4 hydrogen atoms, 4 oxygen atoms, 4 oxygen atoms. So no atoms were created or destroyed in this process. They were just rearranged. That is the definition of a chemical reaction. Atoms are not created, nor are they destroyed. They are simply rearranged. So to write that as a balanced chemical equation would be to write CH4. Notice the subscript tells you how many are in that molecule. 2 O2s, 2 oxygens stuck together, that's your subscript, and there's 2 of those sets. CO2 as a product, and 2 waters. The coefficients out front, those big numbers, they tell you how many of those you have, and notice they are not stuck together. And then the subscripts tell you how many are stuck together. We can also look at the mass in this chemical reaction. So we have a conservation of atoms, and we also have a conservation of mass. So each carbon has a mass of 12.01, each hydrogen 1 times 4, and each oxygen 16 times 4. So if you calculate the mass for the reactants and products, those are the same as well. So knowing that these atoms can't be created or destroyed, they're only rearranged, allows us to do calculations in which we figure out how much of a reactant or product would be required or made. For example, if we know that a car burns 246.4 grams of methane on a particular trip, we can determine what mass of water would be produced because water is a product in the burning of methane. So we'll pick back up here next time looking at that stoichiometry that requires us to go across the map when we have a chemical reaction involved.